So in this video, I want to talk about drawing force diagrams or free body diagrams and how we approach that when we're doing a problem. It's actually really important that you learn how to do a free body diagram. Without that skill, it becomes extremely difficult to do these problems. And so my first word of advice is when you are looking at these problems, draw a picture. It doesn't have to be pretty. If I haven't convinced you with my horrible drawings that your art ability doesn't matter, you're gonna just have to take my word for it. You need a picture so that you can label the forces that are acting on the object and then use those to apply Newton's laws. So let's take a look at these free body diagrams. First of all, let's just think about how we might draw a force vector. In this scenario, we're pulling on a box at an angle. And so when we draw the force, we should pay attention to how big it is and also what direction it's in. Now, to be honest, if you're drawing, the length of your vectors they're not to scale, it's okay. It'll be okay because you'll use the math to figure out which one is bigger than the other. But it might be nice to have some approximate sort of indication of how big forces are relative to each other. What's really you can't ignore is what direction do these forces act, because your picture will help you use Newton's second law or first law, depending on the scenario, to accurately find the relationship between the forces that you have identified as acting on the object. So here's a picture from your book, and what I want to emphasize when we are talking about free body diagrams is that we always have a point of focus. We want to know what are the forces acting on this object. And sometimes that can be difficult because there might be other forces that we want to talk about, but they're not actually acting on the object that we want to analyze. So here's an example where they're moving an object into a building using a crane. Now there's a couple forces labeled here and that are acting on the object that they're moving. Let's call it a piano. I forget what it is, but it's big. So forces that they've labeled is the weight, then the tension, and then this F sub t. And let's talk about what those forces are. The weight is actually the force of the weight of the piano, and so that force acts on the piano. The tension is due to the straps that are pulling up on the piano, so the tension is also a force acting on the piano. However, because of Newton's third law, as we're pulling up on the straps are also pulling down on the crane. And that's what the F sub t is standing for. That is the force that the straps are pulling on the crane with. So, as we'll see in the next slide, that F sub t is not a force that belongs in our free body diagram because we're concentrating on the piano, and F sub t is the force that is acting on the crane. So here in this picture, they are talking a little bit more about these forces. But if I wanted to actually only deal with the forces acting on the piano, you can see what our free body diagram would end up being. I'd have the tension pulling up, and I'd have the weight pulling down. And those would be the only two forces that I would be dealing with. I would then, if I was doing a problem, I would say, okay, now I'm going to look at forces in the y direction. And let's say that the piano is not moving up and down, and so it's in equilibrium. And I would say tension was positive, so because it's up. The weight is negative because it's down. And they are going to be adding up to be 0. So you see that these two forces are replacing the sum of the forces. This is just carrying the 0 down. And so from this, we would say that the tension would be equal to the weight. So here's another example of where we might draw a free body diagram. Like if we're talking about the box on this surface, the forces we might identify on the box would be the normal force acting down, and I'd also have the weight acting downward, mg, or w, whichever you want. And so a lot of times in our book, they draw these free body diagrams and they just replace the object by a little dot. And that's okay if you want to do it like that. I prefer to look at the picture of the object itself and put my labels on there. So both of these could be a free body diagram for this scenario. Here's a scenario where the box is on an inclined plane. Now this time we have, okay, so right here is the normal force. I don't know why they just drew one arrow here. They drew the normal force here. The weight acts straight down because that's how gravity acts. And then the friction is going to keep it from going down the incline. And so whether it's sitting on the incline or sliding down the incline, the frictional force would have to be against the either impending motion or the actual motion. And so again, you can see that this might be a way that we draw the free body diagram, but this is okay as well. I prefer this, but I'm not going to be mad at you if you do this. Now finally, I want to look at something that's a little bit more complicated, because we're going to be talking about like how do we actually use these pictures and sort of incorporate them into Newton's first or second law. This is going to be a problem with equilibrium, and that is nothing's moving. So the acceleration is 0. I say that this is an equilibrium because I'm assuming that the stoplight is going to stay up there up above the ground. It's not going to fall. So if I wanted to do this problem and analyze it, the first thing I would do is identify the forces that are acting on the stoplight. And here you can see they've been identified. There's the weight acting down. There's the tension in this rope right here. They've called that T2. And there's a tension in this rope, and they're calling that T1. And so we're focused on the forces acting on the traffic light. And so you can see that they've done their free body diagram off to the side here. It's exactly the same as drawing the forces on the actual picture. Either one is fine. Now, what am I going to do with that information? I'm going to say that the forces in the x direction are 0 and the forces in the y direction are 0, because I said this was in equilibrium and I need to break these forces down into their x and y components. Now, when I'm looking at this picture, I can see that the tension in the supporting cables are the only forces that have x components. And so T1 is pulling off to the left, and so I'd have minus T1, and its x component would be given by the cosine of the angle that it makes with the horizontal, which is 30 degrees. I'd also have T2, but T2 acts to the right, and its x component would be T2 times the cosine of 45. And both of those x components of tension have to add up to be 0 because it's in equilibrium, and so I'm done with that. Now in the y direction, I want to do it down here. In the y direction, I have not only the two components of the tension that also pull up, but I have the weight that acts down. So the y component of T1 is going to be T1 times the sine of 30, and it's positive because it pulls up. The y component of T2 is T2 times the sine of 45. And then finally, the weight acts down, mg, and those are equal to 0. And so now this is how I would be utilizing Newton's his first law, which is if things are in equilibrium or the net force is 0. And I'm substituting in the forces, and this is where I would be able to start to calculate and find answers. For example, I might be told the weight of the traffic light, so I would know what mg is, but T1 and T2 are my unknowns, and so I would have to solve for them. When I get to this point, it's just an algebra problem. For instance, I could say that T1 would be equal to T2 times the cosine of 45 divided by the cosine of 30. I could then take this expression and substitute it into the y expression, and then I would be able to solve for T2 because I would eliminate T1. And then, once I knew T2, I could come back here, put it in here, and figure out what T1 is. I wasn't going to really do all that math because I wanted to just talk about how we do the diagrams, but this was a nice example to sort of get started on how we're going to apply those equations and do some problems. So hopefully this gets you started.